Hey Ramblers! This video covers chapter 5.4 in our textbook and deals with theorems about definite integrals. Now that we know what a definite integral is, and we've learned the fundamental theorem of calculus, we want to learn a couple of properties of integrals that are going to help us manipulate them and to evaluate them. So this video will introduce you to 4 really useful properties of definite integrals. Then we're going to look at a couple of applications of integrals. The first will be how to find the area between two curves on a graph, and we'll use integrals to do that. And the second will be another really useful application of integrals, and that is finding the average value of an entire function. Not just a list of numbers, but of a continuous function. Thanks to calculus, none of it's really very hard. So please, pause the video often. Thanks for watching. Now that we have learned what a definite integral is, we're going to need to learn how to manipulate them, which means move them around, in order to solve problems involving them. We're also going to start learning how to solve them by hand, but that's maybe the next chapter. For now, let's just take a look at some of the properties of definite integrals, and we'll start with these first two. The first one says that if you switch the order of the limits, notice how the integral on the left side has limits starting at a and ending at b. Well, if you switch those limits so that now you are starting at a higher number, b, and going to a lower number, a, that the sign of the integral changes. Let's take an example. I think sometimes it just helps to look at a picture. So let's take this picture down here. I have the integral of 2x plus 1 from 1 to 5. Now, if I evaluate that integral, I'm going to find the antiderivative of 2x plus 1, which is, of course, x squared, because that's the antiderivative of 2x, plus x, because that's the antiderivative of 1. This line here means I'm just, evaluated at 5 minus 1. So I plug in 5, and I get 5 squared plus 5 minus 1 squared plus 1. Well, of course, that's just going to equal 30 minus 2, or 28. Now, what happens if we switch the order of the limits? Let me show you. As you can see, nothing happens with what the antiderivative is. That's still x squared plus x. But now the order that we're going to plug in the limits changes. You can see that now we have 1 squared plus 1 minus 5 squared plus 5. So 2 minus 30 equals negative 28. So just as the property states, when you flip the order of the limits from 1 to 5 to 5 to 1, you change the sign of the integral. Not the magnitude, but the sign. Okay, let's take a look at the second property. The second property is really just basic addition. It says that if we add the integral from a to c of f of x to the integral from c to b of f of x, we get the integral from a to b of f of x. Well, that's honestly not very intuitive looking in algebraic form, but if we take a look at a picture down here, we see that the first integral from a to c, and this should be labeled f of x up here, plus the limit from c to b is obviously going to equal the integral from a to b of f of x. So what you really have to be careful of is just make sure that your limits, when it goes from a to c, that the next integral starts with c, so that these two, the upper limit of the first integral and the lower limit of the second integral have to be the same number. The two integrals have to be joining or bordering each other. Okay, let's take a look at 2 more properties. Okay, the second pair of properties is also pretty intuitive. If you have 2 different functions with the same limits and you're adding them together, then the integral is just the sum of each individual function. Now, this might not seem like it's terribly useful, but imagine you have the integral of something like 2x plus tan x, and we're looking at 0 to 3. Well, I don't know what the antiderivative of tangent is, but I do know the antiderivative of 2x. So I could break that up into x squared, evaluated from 3 to 0, plus the integral from 0 to 3 of tan x. So now I can simplify that one step further, and this is going to be 9 plus the integral from 3 to 0 of tangent of x. So you see, it didn't make it a lot easier, but now I have a smaller part, just this integral from 3 to 0 of tan x, that I must now solve. In light of the fact that many integrals that we run into we can't solve, we don't have antiderivatives for every integral out there. Sometimes we need steps like this to make it a little easier. Okay, let's take a look at that second property. Okay, the second property states that if you have a constant function or a constant multiple inside of an integral, you can pull that constant outside. And that's also kind of handy sometimes, just to simplify integrals before we anti-differentiate them. So imagine we had the integral of, let's say, 2 sine x. So let's put that 2 on the inside. So 2 sine x dx. We could rewrite that with the constant multiple on the outside. So we had 2 times the integral of sine x dx. Now, that's just going to equal the negative 2 cosine x. But you can see that taking the 2 out in front made it a little bit easier. All right, it's a handy little trick. Maybe you use it, maybe you don't need to, but it's there for you. Okay, let's move on and take a look at the next application of these integrals, and that is the area between curves. Okay, this next truth, or it's not really a theorem, but it's if you're looking for the area between two functions, let's say they are f of x, that one's on top, and g of x on the bottom, and you're interested in knowing the area between them starting at A and ending at B. Well, in order to find that shaded region, you just subtract the integral from the lower limit A to the upper limit B of the higher function, or the function farther up on the y-axis, minus the function lower on the y-axis. Now that's probably pretty intuitive, but it holds true even if the functions are negative. So let's say that our f of x is still above g of x on the y-axis, and we want to start at A and end at B. This region between the two functions is still described by f of x, the integral from A to B of f of x minus g of x, which means there's nothing extra to memorize. It's just the function that is higher on the y-axis minus the function lower on the y-axis. Okay, let's take a look at an example of how all this applies. So here we're going to try and find the area of the shaded region which exists between two parabolas, one opening upward and the other opening downward. So as you can see, we have a upward facing parabola, which is g of x, and that's x squared minus 4x plus 5. We also have a downward opening parabola, which we call f of x, and that's negative x squared plus 4x minus 1. So we want to find this shaded region, and the calculus is going to help us to do that. But the first thing we need to do is learn what are these functions, what are these limits a and b. And in order to do that, we just have to set g of x equal to f of x. When I plug in the two expressions for the functions, I just have to get all the x's to one side and set it equal to 0. I'm going to factor out a 2, and I'm left with x squared minus 4x plus 3, which of course is going to factor to x minus 3, x minus 1. When I solve for x, I get x equals 3 and 1. So those must be my two intersection points. So in order to find what this area is, I'm just going to use the integral from 1 to 3, because those are where the two curves intersect, and I take the higher curve. Now, even though it looks like negative x squared would be smaller, in this case, negative x squared is above the positive g of x, so that once again, f of x is greater than g of x over the interval from 1 to 3. So my integral just becomes the integral from 1 to 3 of f of x minus g of x. They then simplify that, and in a little bit we'll learn how to do this by hand. It's not a terribly difficult one, but they've used a calculator and found that it's 2.667. Okay, Ramblers, let's take a look at the last application here in this video, and that's going to be the average value of a function. The average value of a function is a formula that's very useful and frankly pretty easy to memorize. We just take whatever the function we're trying to find the average value of, in this case f of x. And if we wanted to know the average value from a to b, we would just take that integral of from a to b of f of x. But this time we would divide by the length of the interval. That is to say, we multiply by 1 over b minus a times the integral. Now that's an easy enough formula to memorize, but let's take a look at where it might have come from. So consider the diagram down at the bottom. This entire region is the area under the curve of f of x. Well, that area is described by the integral, and that integral is the integral from a to b of f of x dx. Now, one way of calculating that would be to multiply the length of the base, which is b minus a, times the height. Now, we can't multiply by the total height, that would overestimate it. And we can't multiply by the lowest height, that would clearly underestimate it. But if we measured by the average height, then that would overestimate a bit, but also underestimate a bit. And that could actually equal the actual area. So the average value of the function times the length of the base will give us the area. That's just kind of the area, like base times height equaling a rectangle. So in order to get to our formula, we're just going to divide both sides by b minus a. And dividing by b minus a is the same as multiplying by 1 over b minus a. So maybe that still doesn't click, but that's okay. It's an easy enough formula to memorize whenever you're looking for the average value of a function. Just take the integral of that function and divide by b minus a, or multiply by 1 over b minus a. Okay, Ramblers, real quick example, and then we'll wrap this video up. Okay, this last example asks us to interpret these two expressions at the bottom. And it tells us that C of t represents the daily cost of heating your house, measured in dollars per day, where time is measured in days. T of 0 corresponds to January 1st, 2008. So, what does this first integral mean, and what does this second expression mean? Well, just as the exercises lately have pointed us, we know that this first integral is going to, since it's an integral where C of t is represented in dollars per day, and the dt kind of represents the time, so we can say that that's days. So this integral, if we just look at the units, the integral is going to represent dollars. Okay, so that's the total amount of money it costs to heat your house from January 1st until 3 months, till 90 days later, till three months later. Okay, the second integral is if we know that the integral portion is represented with dollars as the units, and 1 over 90 is going to be 1 over days, because 90 minus 0 is the days. That means that this integral, or this expression I should say, the units for it is dollars per day. Well, that's an average. So while the first integral represents the total cost to heat the house for the first 90 days, the second one represents the average cost per day. And that is the difference between the two expressions. Okay, Ramblers, a lot of stuff here. Hopefully the video is broken up for you so you can understand it. Thanks for watching, and I hope this helped.